First, let me explain. I couldn't get the original title of this post. It is about logistic regression with large P and large N. N means the sample size and P means the dimension. So let's first deal with the logistic regression with large N. So sample size N is large. And you're going to find out if you load your data into R, you get a lot of issue about memory because R will load the whole data into memory. That usually means you don't have enough memory to to do the other work. If you encounter this issue, what you can do is there are some big something R packages available, like big memory, big analytics. The whole rationale for those big something package is that we don't want to load all the data, the N by P data matrix. We don't want to load it into our memory. We only load some of them if we need it. So for example, if you do linear regression, all you want to compute, suppose our N is like 40 million, but P is only 10. So you're running a linear regression model, your data matrix, your design matrix X is a tall and skinny matrix, very tall, because you have like millions of rows, but you only get 10 columns or 11 columns, depending on whether you want to count the intercept. So if you look at your calculation for your beta, which is a P, let's say P already include the intercept, P is 10. All you want to compute is the P by P matrix, which is X transpose X. That's the part involving sum over millions of observations. And the X transpose Y, that's a P by 1 vector. So that's all you want to compute. And so instead of load all your data X into your memory, you can just calculate this P by P matrix, X transpose X, by load some data from read something from your Excel file, and then dump it, read something again. So for example, what you can do is you, So what you need to do is, for example, how you calculate X transpose X, you just run through a loop, and then every time you just add like the column vector times transpose. So just sum them together, they will give you X transpose X. In this case, here I write everything because I still have my X in my memory, but if the original X is very large, you don't need to load the whole X into your memory. Here you can just read, in your loop, just read the ith row from your Excel file, or read maybe 10 rows from your Excel file, and just do this calculation. You don't need to store the whole X in your memory, right? Similarly, you can get your X transpose Y, which is a p-dimensional vector. I call the new Y. Again, this can be done without loading the whole data matrix into your memory. So this is for linear regression, but for a logistic regression, that's the same idea, because inside logistic regression, all we do is just weighted least square. Let me make sure I'm recording this. Okay. So here I just show you, it's so easy to just code your own Newton-Raphson algorithm. You start with some initial value, you go through this iteration, and here I set maximum iteration is 50. Actually, you're going to find out this stopped very quickly. And I tried the threshold to be 0.001, and the iteration stopped after 19 iterations. So this is just a Newton-Raphson algorithm, which you can find out from the lecture notes. Inside just tell you, again, this is the idea of getting those matrix, getting those weights. You can do all the calculation without loading the whole data matrix in your memory. At the end, I show you can compare the beta from my calculation versus the beta from R, and they're very close. Okay? So in summary, if N is really large, there is a way that the real computation cost is in terms of P. So you can actually code your own logistic regression without loading the whole data into your memory. But when P is really large, indeed you're going to have an issue, because in our Newton-Raphson involves inverting a P by P matrix. Then what you can do is just, instead of using the second order approximation where involving the Hessian matrix, you just do first order, meaning you work with your logistic regression, your log of the likelihood function to calculate the gradient, which is a p-dimensional vector, and just move a small step along that gradient. That's your new beta value, and calculate your gradient again and move a small step along that direction. So that's sort of the basic algorithm for a lot of machine learning machines nowadays, like deep learning. They all just do gradient descent. There is another way to do stochastic gradient descent, meaning when you compute that gradient, because our loss function is a sum of our log loss over n observations, right? Because our log likelihood is a sum over from 1 to n, the log likelihood over the ith observation. So this is our loss function. When you calculate gradient, you still need to do that summation over n. If n is millions, there's still a lot of computation. So this is now more like up-to-date computation strategy is using stochastic gradient descent, meaning you're going to treat this sum, if you divide it by n, that wouldn't change the minimizer or optimizer. This becomes the expectation. Then instead of calculating the whole expectation, you can take a batch, which means a small subset from this training data, or even just randomly pick one observation and calculate the gradient of the log likelihood at that particular observation. Because if you do this many, many times, in long run, the expectation will approach to the truth. So this is stochastic gradient descent. And what you gain is, instead of evaluating your gradient, when you compute your gradient, instead of doing the gradient over n observations, you can only do the gradient over a small set of them. So that saves a lot of computation. And in terms of the corresponding algorithm for that, you can just do a Google search, and you can easily find a lot of R code or Python code available. It's very easy, and probably just 5 or 4 lines. So you can use that one. Okay, so this is for logistic regression, and let me switch back to SVM. But before doing that, I want to answer that question, because there's a question on the discussion forum asking about the forbidden direction. So when we're talking about SVM, the problem, underlying the optimization problem, but it is an optimization problem with some constraints, actually inequality constraints. So when we talk about inequality constraints, when we talk about Kkt conditions last time, we sort of review all those conditions. We start with the basic optimization. There's no constraint. You want to minimize a function fx, where your x could be any, your x could take any value. This bother you? This one? Okay. Okay, so this is the best I can do. So you want to minimize function f, and x could be anything. Now, how we approach this problem? We take the derivative of f with respect to x and set it to 0. The rationale is that if x is a local minimizer, if fx is convex, then local is the same as global. Let's just talk about general case. If so, any x which is a local minimizer, which is like one of the candidates for the global minimizer, and that local minimizer must satisfy this condition, because if you achieve the minimum, that means if I take derivative, and we know if there's a direction which is a derivative. If I go, if I move a small step along the negative of the gradient, so minus the derivative, that if I move a tiny step along that direction, I should be able to decrease the value of f, right? But because locally you are minimal, so there's no way you can take that step. That means that direction should be 0 direction, does not exist. So this is a rationale for this condition. When we try to optimize a function, we always look at the derivative and set it to 0. Okay, so let's look at the second problem. Now is again minimize fx respect to a equality constraint. Okay, so the equality constraints means that now you are not allowed to find any x to minimize f. There is a feasible region of x. And what are the feasible region of x? All the x, they must satisfy that equality constraint. So gx is equal to b. Okay. Again, we can do the same argument. Suppose x is a solution, or at least a local minimizer of this problem. Then on the left-hand side, that represent which is minus derivative of f, and that's a direction where we know if we take a tiny step along that direction, we can reduce the value of f. And we know that direction shouldn't exist, okay? But in this particular case, that direction may not be zero, but that's a forbidden direction, what I call it. What is a forbidden direction? Because that direction will also change the value of g, right? Because on the right-hand side, I take derivative of g and times a scalar lambda. Here, lambda could be positive, could be negative, and could be zero. But no matter you are going to move step along the derivative, which is lambda is positive, so you're going to increase the value of g, or if you're going to move a tiny step on the opposite direction of the derivative, which means lambda is negative. No matter which direction we're talking about, those are all not allowed because that will change the value of g and you get out of the feasible region. So that means, so this is a sufficient condition for x being a local minimizer of f subject to that constraint. Okay, so here you can see the lambda, there's no constraint about the sign of lambda. Lambda could be any scalar. So things going to be a little bit different when we talk about the third type of problem, which is a problem we really care. We want to minimize fx subject to an inequality constraint. Here our inequality is specified as gx bigger than b. Okay. Now let's assume gx is actually concave in the sense that the feasible region of x is a convex set. So this is a feasible region of x, meaning all the points inside the circle, including the boundary points, they satisfy that gx is bigger or equal to b. Okay, so here we have to talk about two cases. Suppose x is a local minimizer, or at least solve that optimization problem. So suppose that x is inside, this region. That means, gx is strictly bigger than b. So that, if that's the case, we know that we can always place a tiny neighborhood around x, such that the whole neighborhood, all the points in that neighborhood, they satisfy this constraint. So the whole neighborhood is inside the feasible region. Okay. Now then you're going to find out if x is x solving that is a solution to that problem. That means locally there's no direction can reduce the value of f. So if gx is strictly bigger than b, then if x is a solution, we want the derivative of fx to be zero. This first case. Second case, your x is actually on the boundary. So that means your gx is equal to b. Okay? If that's the case, again, let's do our argument. Now there could be a direction that can reduce the value of f. In this case, there are forbidden directions. What is the forbidden direction? Any direction that will reduce the value of g will be a forbidden direction. You're allowed to increase g, because increase g, you're sort of getting into this region. You still are in the feasible region, but you are not allowed to decrease g. Okay, so that means, so that's the this condition. Oops. Here, when my left-hand side, which is shaded in light blue, is a direction will minimize f. But the right-hand side, let's assume right now lambda is strictly positive. So right-hand side, I do have a minus sign in front of it, and lambda has to be positive. And that represents a direction, it will decrease gx. And that's a forbidden direction, okay? So we can actually put two cases together by also allow lambda to be zero. But lambda can only be zero if this is true, right? Oh, sorry. Maybe I should, lambda could be zero in this case too, but And when this is true, lambda cannot be, let me think about this, right? Right, so if gx is strictly bigger than b, lambda has to be 0 because, yeah. So you put these together. So let's look at what is the so-called Kkt conditions. So the first condition, you can think about is actually the derivative of the Lagrangian respect to x to be 0. So how we define the Lagrangian is an objective function, be careful, always minus lambda times the constraint. And the constraint must be specified as the constraint is bigger or equal to 0. Because for the third type of problem, signs are very important. Okay, so your Lagrangian must be specified this way. Objective function minus lambda times the constraint, and the constraint is specified that way. And so the first condition, that equality is just the Lagrangian take derivative with the argument of the original problem. And lambda is a Lagrangian multiplier. And the remaining two conditions, lambda bigger or equal to 0, that's a requirement. Lambda has to be non-negative. And the third condition, just restate that constraint, because gx has to be bigger or equal to b. And the last condition is so-called the compatibility condition, meaning when the constraint is not active, meaning gx is strictly bigger than b, then lambda must be 0 to make the whole thing, the product, to be 0. Okay, so the last condition, just to now put the two cases as one, which is the first condition. Okay, so this is the Kkt condition for constraint optimization. And just remember, once we deal with the constraint optimization, we want to minimize, and constraint are specified as bigger or equal to 0. Then define your Lagrangian this way. So Lagrangian involving two set of parameters, arguments. The first set of argument is the argument of the original optimization problem. And the second set of arguments, here's only one, which is a Lagrangian multiplier. It's defined this way. And then you're going to start and list those Kkt conditions. First condition is a derivative of L respect to x is 0. And then Lagrangian multipliers must be non-negative. And then third condition, just restate the constraint. And the last condition is a compatibility condition. So that's all the Kkt conditions you need for constraint optimization. Okay, good. So now let's look at, just review what we have learned. And wait, did I miss the page? Yeah, oh, I think it's fine. So let me review what we have learned previously. We are talking about linear SVM, meaning we are given a data in a p-dimensional feature, here p is 2, and they are separable, meaning I could draw a line and divide the two groups of data on two sides. So that's my solid blue line. There could be multiple ways to separate them, but what we are looking for is, we're not looking for just one line, we're looking for an avenue, which is the two sides are the dashed lines. An avenue we can place between the two sets of points. And we want this avenue as wide as possible. And that concept is what we call the margin. And so we went through some of the mathematical details and figure out a way to parameterize those three lines. And we also find out the margin, half of the weight of the avenue is 1 over the L2 norm of beta. And then we formulate our max margin problem. We wanted to maximize 1 over the norm is equivalent to maximize the norm, and equivalent to maximize the norm square, and it's equivalent to maximize half of the norm square. So that's our function. That's the function we wanted to maximize. And subject to the constraints, because the problem is formulated in a way that the two group of points are well separated on the correct side of the two dashed lines, right? So this is the problem. Now, this is a convex programming problem. In particular, the objective function is a quadratic function, and the constraints are linear constraints. And something nice about the convex optimization is any local optimal going to be global optimal. And now, the next two statements are very crucial. We're going to talk about three problems: the primal, the dual, and the Kkt conditions. And they are all equivalent in the following sense. Okay? I know this is a pretty busy slide, and so let me talk about the three boxes. This is a primal problem, right? We wanted to maximize the margin subject to the constraints, and the parameters or the arguments are the slope, p-dimensional beta, and the intercept, the beta 0. Although beta 0 does not appear in the objective function, but actually is in the constraint, right? So for the primal and our arguments or the parameter we aim to estimate are p-dimensional, p plus 1 dimensional, which is a linear function. The coefficients and intercept. But what we want to solve is actually the dual problem, because the primal is a constraint optimization, so we can define the corresponding Lagrangian function. The Lagrangian function involving two sets of parameters, right? The parameters in blue are the parameters from the original primal problem, betas. And the parameters in red are the Lagrangian multiplier, one for each constraint. We have n constraints because there are n data points. They have to be put on the correct side. So we have lambda 1 through lambda n. And the Lagrangian function, just put them together, objective function minus lambda I times your constraint, which has to be bigger or equal to 0. And you can reorganize it. So instead of solving the primal are objective function involving betas, we actually solve the dual problem. And in dual problem, the objective function, the parameters are the lambdas, lambda 1 through lambda n. Okay, so there are two sets of parameters, but they are linked to each other through the Kkt conditions because they're all equivalent. Primal and dual for this particular problem, they're basically solving the same kind of optimization problem. And the two are related, but there's a kind of a mismatch between the primal and dual because the variables are different. Okay? One is over beta and another is over lambda. But they are linked to each other through the Kkt conditions. Once we work with the dual problem, we solve those lambdas. We plug into the first equation from the Kkt, we get our beta, which is slope, p-dimensional. And then you're going to find out some of this equality going to be exactly 0. That's where we can retrieve the beta 0. So you can solve beta and beta 0, get your primal problem. Now, why we want to work with the dual problem, it's actually easier to solve because if you look at the appendix I also mentioned previously, you can get rid of the first condition. And you are dealing with a quadratic function, and there are n parameters, lambda 1 through lambda n, and the only constraint you have is just lambda i's should be non-negative. So that's a pretty relatively easy problem to solve. And second property about the dual problem is, although we have lambda 1 through lambda n parameters, but most of them are going to be 0. Because lambda i's are the Lagrangian multiplier, right? So Lagrangian multiplier, and because this the last condition in Kkt, that's a compatibility condition, means the lambda i's will be non-zero if the expression inside the bracket is non-zero. Okay. Wait. The lambda i's will be 0 if the expression inside the bracket is non-zero, because the product should be 0. If the expression inside the bracket is non-zero, then lambda i's must be 0. Okay, but under what kind of condition that the expression inside the bracket is not going to be it will be non-zero? Inside the bracket basically represent the two dashed lines. So if you are not on the dashed lines, that means you're going to be, for example, the top three green lines, they're going to satisfy beta times x plus beta 0 strictly bigger than 1. Or if you're on some of the red lines, and they're strictly less than -1. Here, I do have a green this one is on the dashed line, and I should move this red one and a little further. That one is also on the dashed line. So there are only 2 points on the dashed lines. So only those 2 points on the dashed lines, their lambda i's are non-zero. So that means when we solve this dual problem, when we try to find out our beta, remember we sum over I is supposed to from 1 to n, but actually we only need to sum over 2 observations, because only 2 observations, the lambda i's are not zero. And they are known as the so-called support vectors, SV. So support vectors represent data points, and they have non-zero Lagrange multipliers. There are only a few of them going to have, they are non-zero. And for this particular setup, they are the data points on the dashed lines. So the whole model is kind of a simple in the sense that it is sparse in a different way. So the resulting beta at the p-dimensional coefficient vector, there's no guarantee that one is going to be sparse. What's sparse is that beta can be written as just a summation over 2 of the kind of scaled version of the corresponding x vectors, only involving 2 x vectors. Okay, because your beta is equal to sum over I, the i's from the support vectors, and yi, xi, and these are lambda I. So this is a p by 1. Lambda I and yi are the scalars. Okay, so it is sparse because only few of the lambdas are non-zero. And I will talk about why this is relevant to kernel trick later. Just to summarize what we have learned so far, this type of problem is known as a hard margin problem for SVM. So this is a map I will, on the right-hand side is something we're going to cover for the remaining of the lecture and in the future. So what we have covered so far is linear SVM for separable data. The data have to be separated. Otherwise, if the solution does not exist, the Kkt condition is just useless because those are only relevant if there exists at least a solution. So for linear SVM with separable data, and we formulate our problem as finding a decision which is a solid blue line to separate the 2 groups of data. Oh, by the way, once we solve this SVM, once we solve beta and beta 0, which is the blue line, how we do prediction when a new test data comes in, we use this solid blue line to make our decision. If you're on the green side of the solid blue line, even though you might be on this avenue. So suppose we have a data point here. We're going to classify that data point as green. If you are below the solid line, you can classify as red. So although we formulate the problem with that dashed lines, but for the final decision making, it's based on that solid blue line. The decision is only one line. So this is linear SVM for separable data. Just again, quickly summarize the flow. We formulate this max margin problem, which is our primal problem, and the parameters we aim to estimate is p plus 1, right? Linear function. But then we actually solve a dual problem where we solve Lagrange multipliers, lambda 1 through lambda n, at dimensions n. So this is why you're going to find out if you are working with a data set with only 2 features, but you have 4 million observations, your computer is going to crash if you want to use SVM, because the computation cost for SVM is in terms of sample size, not in terms of the original dimension p. Okay. And so how the primal and dual problem are linked? They're linked through the Kkt condition. So there's 3 elements: primal, dual, and Kkt. They're all equivalent in some sense. They all try to characterize the underlying solution. We also get the concept of support vectors, because the solution only depends on those support vectors. They are the data points on the dashed line. For example, suppose in this case, we have only 2 support vectors. If I remove, I remove this data point, and my decision boundary should stay the same. Or if I move this data point somewhere else, and the decision boundary stay the same. So it's a pretty robust solution. So this is what we have covered so far. It's known as a hard margin because we're going to move to the case where, for example, look at this example. You can try to think about whether you can find a line to separate the two groups. Can you separate the two groups? Can you? This way? I don't think so. So this is an example where you cannot separate the two groups using a line. So how are we going to deal with that? One type of approach is to, people will draw something like this. If we cannot separate two groups of data points, we're going to work with the so-called soft margin, meaning we're going to allow you to make a mistake. So in this case, we still want to place a wide avenue between the two groups, but there are two green points. They're on the wrong side of the dashed line. There are going to be error involved. So eventually, we're going to minimize the objective function, which is a combination of the margin and the error you're making. So it's a weighted sum of the objective function going to be a weighted sum of two terms. Another extension is go with so-called Kernel Masters. The idea is to, because you probably can use a quadratic function to separate them, right? Use a smooth curve. So the idea is just try to find, instead of looking for a linear decision boundary, you want to look for a nonlinear decision boundary. And something interesting is that instead of formulate your nonlinear function, nonlinear function, what you're going to do is you're going to take your data in the p-dimensional space. Here's 2. You embed into a higher dimensional space. And then turns out you don't even need to visit the higher dimensional feature space as long as you know how the inner product are calculated. So that's known as the kernel trick. So the both soft margin and kernel machines are regarded as an extension of dealing with non-separable data. But turns out you can use them on separable data too. Meaning, even if data are separable, you still want to do that argument. Maybe I can make my avenue wider while allowing some observation to make some errors. Just move to that margin plus an arrow kind of a framework. So this is why both soft margin and the kernel machine can be used to deal with separable data too. And there are some practical issues. One is in SVM, we are directly looking for the decision boundary. Once we find our solid blue line, we make our decision. On this side, you get 1, other side, you get -1. But there's no probability, right? So there's how we go with binary decision boundary to probability. And another is everything's binary class, how we go from binary to multi-class SVM. And I will mention that at the end. And actually some of the references I attached, I linked to Piazza have already addressed some of the issues. Okay, so I'm going to first move to soft margin setup. We have data in two-dimensional. Now we cannot separate them by a linear function, but still let's put a one candidate avenue. The blue lines, solid blue line in the middle, and we have 2 dashed blue lines. And we notice there are 2 green data points that are making mistakes. We have those purple dashed line represent how far you are away from the correct decision, the correct dashed line. So the objective function becomes, this is the first term, the quadratic term is actually not a sort of transformation of the margin. So we wanted to maximize margin means minimize some kind of transformation of the margin. And the second term is the error term. Gamma is a tuning parameter you have to specify. It's a weight. Represent how you're going to weight the 2 type of quantities in your utility function, because you want to minimize the weighted sum of both. So what is the error of psi I? For the green points like this, we know they correspond to beta x plus beta 0 strictly bigger than 1, right? Because they're on the correct side. Now, for those 2 points, for example, for this one, you know this one is not bigger than 1. But we are going to introduce some slack variables, meaning it's okay, let's just, allow you to, for you, we're going to relax this 1, or allow you just bigger than 1 minus psi I. Okay, so the psi I is positive in this case. Of course, if psi get large, it means you're really further away from the correct dash line. So you wanted to minimize those psi i's. Okay, and for points like here, you don't need psi. You could add a psi I here, but the psi will be 0 because you want to eventually minimize the sum of the psi. So automatically, if you're on the correct side of the dash line, those psi i's will be automatically set to 0. Okay, so this is our objective function. So it's a sum of the 2 terms. And now the only difference from when we compare this soft margin versus the hard margin is now in our objective function we have a gamma and times the sum of the error psi i's, and the psi i's are introduced as a slack variable because previously we want that inner product of yi and that parenthesis is strictly bigger than 1, but now it's bigger than 1 minus psi I. And sometimes we need the psi I. For example, in these 2 green points, we need non-negative psi I. Okay, so this is our objective function. Again, it's not too difficult because the objective function is still a convex function, and constraints are convex constraints. So I'm going to show you a very scary. Not yet. So I want to point out the problem, the primal problem, the soft margin problem with slack variables is still a convex programming problem. Well, I want you to notice that we have more constraints. So there are n constraints and another n constraints, so 2 n constraints. But still a convex programming problem. So local optimal is a global optimal, and then we're going to have that equivalence among those 3 elements: primal, dual, and the Kkt conditions. Okay, so let's move to this slide. I call it scary slide. Primal, right? And here, I do want you to notice we have some new parameters now. For the primal problem, we have our p+1 parameters about the linear decision boundary, beta and beta 0. We also have psi 1 to psi n, the loss, the error, right? So the parameters in blue are our, are the parameters for the primal problem. I color that gamma in red, just remind you that it is a tuning parameter. You have to specify. Of course, in practice, you can use cross-validation to choose gamma. So beta 0, and psi 1 to n will be the argument for the primal problem. And we have how many constraints? We have 2n constraints. So we have 2n Lagrange multipliers, lambda 1 to lambda n, and eta 1 to n. Now, bear with me because eventually actually it's very easy. So here my Lagrange multiplier. The first 2 terms are copied from the objective function from the that objective, which is the objective function of the primal, and then we minus lambda I times the first set of a constraint, and then minus eta I. Oh, sorry, there's a psi I. Right. So and eta I times the psi I because we have 2n constraints, right? So let's just do some simplification. The first term copy down, and then we take this term all the way to -1, which correspond to those 2 terms, right? Because sum of the lambda I times this minus this plus sum of lambda I, and the remaining terms are related to psi I. So have a sum over psi I, but there's the term in front of psi is gamma, gamma, we have minus lambda I, we have minus eta I, right? So they all together becomes the last term, right? I actually going to find out this one you can just ignore because it's equal to 0 once we go through the Kkt condition. So you're going to find out once we get rid of the last term, the previous expression is exactly the same as the Lagrangian function we encountered for the hard margin problem. Just switch back, right? That's exactly the same. Okay, so what are the Kkt conditions? There are 3 groups of, well, actually 4 groups. You cannot see the color. You can see the color on this slide. What are the Kkt conditions? We have our Lagrange function. Take derivative with respect to each of the blue variables. Set it to 0, okay? So when you take derivative with respect to beta, you get the same result, and also with beta 0, you get the same result as what we got for the with the hard margin problem, because the expression is the same. So you get your first 2 equations. Now you also have additional Kxt i's as your argument from the primal. You take derivative with respect to Kxt I, set it to 0, you get this term to be 0. So the whole term is off, okay? So you get your first 3 equalities are basically the derivative of your Lagrangian function with respect to each of the blue symbols. And then the remaining would be, well, your Lagrangian multipliers must be non-negative, lambda I bigger than 0, eta I bigger than 0. And your constraints must be satisfied, just restate those. And then you're going to, I have Kxt I bigger equal to 0. Oh yeah, Kxt I bigger than 0 is also in the constraint, right? So those 2 conditions are, so those are the derivative. And this just restate your Lagrangian multiplier must be non-negative. And those 2 are just restate the constraint from your primal. And the last 2 are basically the compatibility conditions, right? Right, because compatibility means lambda I times this guy should be 0, and eta I times this guy should be 0, right? So that's all your Kkt conditions. And then you can go, now you can go back to work with your dual problem. The dual problem basically is a Lagrangian function, but you're allowed to use those Kkt equalities from the Kkt conditions to drop some of the green variables, and you should be only left with the red variables. In addition, you can actually drop all your eta i's because this term is off, so eta I is not there. And even if you look at your constraint, the eta I disappeared. Yeah, we don't need eta i's. Okay. Now the only thing is this one. Previously, so the dual problem looks awfully similar to the hard constraint, the original dual problem. The only difference is that previously we only require our lambda i's to be non-negative, but now lambda i's got the upper bound. It's because of this condition. So eta I is a Lagrangian multiplier for Kxt i's. So what are the variables going to have Kxt i's and they are non-zero? Kxt i's will be non-zero if you're either on the dashed lines or you're on the wrong side of the dashed lines. So in this case, there are 4 points. 3 green, 1 red, right? Agree? And so if you're, so those are the points with eta i's to be non-zero. That means, Kxt I to be non-zero. That means their eta i's must be 0, right? That means their lambda i's must be equal to gamma, so lambda i's must be non-zero. So you're going to find out, well, first let me explain why the eta i's have to be upper bounded by gamma, and just based on this this condition. Because this is equal to 0, and your lambda i's and eta i's are all positive, so you just rearrange it, you realize your lambda i's is equal to gamma minus eta I. Eta I is are positive, so your lambda I must be upper bounded by gamma. So that's for the condition here. But what I just described about who's going to have non-zero lambda I, you're going to find out what are the support vectors here, meaning the lambda i's are not zero. There are the data points, not only the data points on the dashed lines, but also the data points on the wrong side of the dashed line, because your Kxt i's going to be. I think I got into a little bit confusion here. First of all, the points, the Kxt I is going to be non-zero, and there are only only those 2 points. So if you're on the dashed line, your Kxt I is actually going to be exactly 0. Yeah. So those are only those 2 grain points. Their Kxt i's will be non-zero, but that means their eta I is going to be 0. But that means their lambda I is going to be gamma. So their lambda i's won't be 0. So this is one type of support vectors. Another type of support vectors are the points that are exactly on the dashed line, but that's sort of similar argument we had before. You're going to find out if they're exactly on the dashed line, and then you're going to find out. So if the Kxt so first let's look at the data points. Let's divide the data points into 3 groups. Okay, first group, those are the points on the correct side of the dashed lines. Okay, and following similar argument we had before, you're going to find out their lambda i's going to be non-zero, because this part inside the bracket. You can find inside the bracket, for those points, your Kxt I is going to be 0, and inside the bracket is a strictly bigger than 0. So their lambda I going to be non-zero. So they're going to be support vectors. Sorry, they're not going to be support vectors. So if you're on the correct side of the dashed line, first category, you cannot be support vectors. We can just ignore you. Okay. And the second type of data points, those are data points exactly on the dashed lines. That's the point we don't know. Meaning, based on the Kkt conditions, we actually don't know about the lambda i's, but at least we know the lambda i's could be non-negative, could be positive. So they could be support vectors. Now, the third type of data points are the data points that are on the wrong side of the dashed lines. And we just went through that discussion. You're going to find that their Kxt I is going to be non-zero. That means their eta I is going to be 0. That means their lambda I is going to be gamma, so it's not 0. So put everything together. What are the support vectors for this type of problem? They are the points either on the dashed lines or the points that are on the wrong side of the dashed lines. Okay? But if you're on the correct side of dashed lines, and similar to the hard margin problem, you don't need to worry about them. They actually won't play a role in the final calculation. What I mean, the final calculation is you're going to solve, so the flow is, we formulate the primal problem. Yes, there's a tuning parameter gamma now. I'm just going to talk about it in a minute. And then you formulate the primal, and you solve the dual problem. You get a bunch of your lambdas. And now you plug in the lambdas into, the first equation, you got beta. In your first equation in Kkt, you got your beta. There's a way you can figure out how to get beta 0, because there are some equality poles with people on the dashed lines. So you are done, okay? And a lot of the summation over I involving lambda I, but only a small set of the data points going to have non-zero lambda I. Those are the data points either on the dashed lines or on the wrong side of the dashed lines. So it's sparse in that sense, okay? Am I running out of time? Oh, 1 minute. Okay. So let's talk about that tuning parameter gamma. It's very confusing. The gamma, because the quiz is really with gamma. So gamma here, the tuning parameter, is the price we want SVM to pay for having a data point on the wrong side of the line. It is parameterized. It's sort of almost just proportional to the C symbol in this SVM in R, which is a software and GSS and paper, and I attached on Piazza. So let's look at the behavior of gamma. So if we increase gamma, okay, if we increase gamma, that means we want SVM to pay a lot of price for having data on the wrong side. You know what? I think it might be useful to first tell you, please stay with me just for another 5 minutes. I think it's worth looking at where's my appendix? Just I want you to know that it's I want you to be aware it is okay to I don't have that. It's okay, like even for this separable case, we could formulate this problem. I have to find out my file. Well, let me just stick to this one now. So if we increase gamma, the SVM needs to pay a lot of price for having the error. So if we increase gamma, then if you increase gamma, that's the price you pay. If you increase gamma, you're going to it's going to make the avenue wide or small? Small. Going to make the avenue small. Small. Okay. But in that case, I think in small, that means you're going to have less number of support vectors. I should really get I have to get that page involved. Just stay with me. This is very important because really with your quiz. So first I want to convince you that even for separable case, you can play the same game, loss and penalty, right? Okay, so in this case, you can find out if you increase the price for having things on the wrong side, you're going to prefer the upper case. You want the avenue to be narrow. When your avenue is narrow, definitely you're going to have less number of points on the wrong side of the dashed line. You're going to have less number of support vectors, okay? And then it actually implies more, your model is more complex, you tend to overfit. Because there's a way, you're going to find out there's an equivalent way to formulate your primal is as the loss plus penalty. Here, your original margin related quantity becomes coefficient. You penalize it with nu. So nu and that gamma are reciprocally related. So when gamma is large, that actually implies small regularization. So it is true your model going to be more sparse, but the underlying model is actually more complex. So I want you to go back to read this part because I just add a comment. You may feel like you run into some kind of a contradiction, but we can talk about next time. So large C means less regularization because reciprocally related with that penalty term, and means overfitting. But large C also means your number of support vectors is going to be small. So in some sense, your model is sparser because you rely on less number of observations. Then you may feel like you're going to, well, that actually should means, based on what we have learned with lasso everything, that means means higher regularization, means good out of sample prediction. But the second argument actually is not really correct. And you can take a look, I attach a new paper here, so 7.4. So the model complexity and the number of support vectors, the relationship isn't that simple. So in short, you cannot use the number of support vectors to argue that your model is going to be more or less complex. Yeah, good.